Hello and welcome to this video series. My name is Akram Ahmed, and in today's video we're going to be talking about search algorithms and in particular adversarial search. What is adversarial search? In adversarial search, we tackle the problem when we are trying to plan and find a goal in multiple choices that we have, but there is an agent, an adversary, somebody who's playing against you, and he's trying to stop you from reaching to your goal. So this is basically adversarial search. When we have some other entity, an agent or a party that is playing against us and trying to stop us from reaching the goal that we'd like to reach. An example of this is the tic-tac-toe game. We used to call it when we were little XO. And the tic-tac-toe game is pretty simple. Let us go and take an example of a tic-tac-toe game. So in a tic-tac-toe game, this is a tic-tac-toe game. And in it you have 9 states. As you can see, there are 9 states over here. And the computer is going to be selecting one state as the first player, and then I will be the adversary, and I will try to stop this computer from winning. So for example, the computer started, it already selected this. I can actually go select this one as an X. Then the computer selected this. So I can actually select this, and then I can see that it's making a line over here, so I'm going to stop it, and then as you can see, the game stopped with no one actually winning. So none of us can actually achieve the goal. So I actually stopped the computer from winning. I can actually make this false. And I can run this code again, and when I run this code again, I am basically the first player. So now I'm going to start playing, and the computer is going to stop me from winning. And this is basically, I put an X over here, and the computer put an O over here, so I can actually put an X over here. Notice the computer is stopping me, and whatever I try to do, it's going to try and stop me from achieving my goal. And notice the game actually stops over here where I couldn't win. I can actually do this multiple times, and I can start from here, and notice the computer is blocking all my moves. So whatever I try to do, the computer is blocking me. And so it's a smart agent, actually, the computer over here, that is trying to block me from winning. And notice it is playing quite smartly over here. And this is adversarial search. And how can we actually do this type of search? So as human beings, when we have games that require adversarial type of playing, just like tic-tac-toe, you might have chess, you might have checkers, all the games that we have, 2-player games that we play, it's an adversarial type of game where you're basically trying to stop the other person from winning by selecting the choices that will try to force that person to lose and will make you to win. And the adversary is trying the same thing. It is trying to win and force you to lose. And if it cannot force you to lose, it'll try to break a tie with you so that you don't win. So that's the best thing it can actually do. So as humans, when we play these games, we have a mixture of analysis that we do. So we look at the board, we analyze, we try to determine what's going to happen and how things can move, what are the possible choices that I have. And we also have strategies, so we might be working with a certain strategy. So especially in chess, let's use that strategy to play. We'll move this piece first, then we'll move that, and you have that strategy. And then you might have some tactics and tricks up your sleeves that you're trying to do, and we try to combine all of this to play the game. For the computer now, to play this game, we need to put these things in the computer, and to do that, we use some sort of if-then rule, and that basically is nothing but a tree. So there's choices that we have to make, and we want in that tree the computer to select those choices, And we want the computer to look ahead. As we do, we often plan 3 or 4 moves ahead. Okay, so if you are an expert in playing chess, you might be planning 10 moves ahead or 15 moves ahead, depending on how expert you are. If you are a rookie, you might be planning like 1 or 2 moves ahead. So if I move here, then he can move here. Then what I'll do this. Something of this sort of in these lines we'd like to have the computer to do, to look ahead and evaluate so it can take better decisions. And we'd like to reduce the search tree. So we don't want the tree to grow very fast because the computers are limited in the resources, in memory, and in processing power. So we don't want this tree to expand and become like having billions of choices in it from which the computer will have to select, because that is going to be too tough for it to start detecting which choice it has to do. So we'd like to reduce the search space as much as possible. And the question is, how will you make the computer win? To do that, we'll start with identifying some basic things that the computer needs to know. So there is something called the initial state, and the initial state is the board position. Okay, so when we start a tic-tac-toe, we have 9 positions which are empty, and that's the initial state. Of course, in addition to that, we need to know whose move is it. Is it my move or is it the adversary's move? Okay, so each one is playing, and we need to know all of this information when we start the game. Then we have the operators, or the operations that we can actually do, and we need to tell the computer what are the legal operations and legal moves that it can do. For example, when you're playing the chess, if you have a position that was already selected, then you cannot select that position. That is a rule, an operation that we need to tell the computer to do it before we can program the computer to play the game correctly. Okay, the computer cannot select any board position that is not on the board. Okay, so sometimes in some games there are some board positions that you cannot select because the piece that you have cannot move that way. Okay, so for example, a pawn cannot jump 5 places ahead. So all of these rules have to be given to the computer so it can actually make the decision. And there has to be a goal and the terminal state, okay, the end state, the goals that we want to do. The goal is to win, and of course we have to give it also the other states that can happen of losing and having a tie. Okay, so we have to tell it when will the game be over. Okay, so for example, if you are playing tic-tac-toe, the game is over either if you have 3 X or 3 O's in a row, or there are no more board spaces left. Okay, so all of these conditions are for the game over. For example, in a chess game, the game is over only if the king is dead. If you have a checkmate and the king cannot move. Okay, so that's only the time when the game is over. Or of course, there could be a game over when the adversary actually surrenders and says, I want to stop playing now. Okay, and there is something called a utility function. What is the utility function? A utility function is a function that we define for the computer so it can determine the best choices that it can actually make. For example, if you win a tic-tac-toe game, you can give the utility of +10. If you lose, if you are in a position that you're going to lose, then you can give it a -10. And if you have a position in which you are going to tie, then you give it, for example, a 0 value. So the computer, when it starts the game, it will try to look and select the choices that will take it to a 10 and avoid those choices that take it to a -10. And if worse comes to worse and it has a choice between -10 and 0, it's going to select the 0. Okay, so the tie instead of losing. So this is how we program computers to see the choices that it's taking, and we call it the utility function, sometimes called the payoff, when you select this move. So we need to measure the outcome of the game. So each step that we do has to have some sort of utility, and the computer, when it plays this game, it tries to maximize the utility. Of course, it's the same thing that happens when we human beings play. When we move a pawn, for example, in a chess, at the first step, we are basically trying to maximize our utility, and we would like to win, and that's why we're playing. Okay, it is at the end of the game when you see, okay, I'm not winning, my strategy was not good enough, I don't have my pieces in the right position, and the opponent has a better chance of winning. It is at that time then we say, okay, can I actually block him from winning, and can I have a tie with him in some sort of a way? And that's exactly what happened in the tic-tac-toe game. We want to maximize our utility, want to win, but the choices that the opponent or the adversary makes us then think of other things and say, okay, well, I'm not going to let him win, so let me make a tie with him so we get a better utility. So these are the utilities, and the search objective is to find a sequence of players' decision or moves in a game that actually maximizes the utility. That is what we are searching for here. A sequence of choices that maximizes the utility. Okay? And in this sequence of choices, you want to consider the opponent's move also. So you need to consider what your opponent will do. So let's take an example, a very small example. Let's suppose that I have a game where it actually is a selection of two things. So if you start the game in a state of S, you can either go to A or you can go to B. Then your opponent is going to play, and he's going to take you from A to C and from A to D. Okay, or if you are at B, he will take you to E, or he'll take you to F. And we've given the utility for all of these different states. So if you reach state, you get 2. If you reach D, you get a 7. If you reach E, you get a 1. And if you reach F, you get an 8. Of course, when we start the game, we are planning to go to the maximum utility, which is 8. However, if you are playing with a smart agent, you need to determine which is the best choice so that you could actually get the maximum out of the game. So if you are at S and you want to go to the maximum utility and you select 8 to be your maximum utility, notice when you go from S, you do the selection B, then the opponent will have the choice of selecting E or F. Now the opponent doesn't want you to get the maximum utility, it actually wants you to get the minimum utility that you can, and it's gonna divert you from B to E, and you will get a utility of 1. Okay, and utility of 1 is the worst utility, as you can see from all the choices that you have. On the other hand, if you started with S and you selected to go to A, and you had a smart opponent that is minimizing your utility, he will have a choice of going to C or D, giving a utility of 2 and 7 respectively. So the smart adversary will take you to C, and you will get a utility of 2, which is a much better number than a utility of 1. And hence, when a smart agent or the computer plays the game, it is going to go to A directly, and then if the opponent is smart enough, he's going to give it a utility of 2, and this is the 2 that you're going to get. You got the maximum utility that you can actually achieve. And this is because if you choose B in the first one, the minimizer will choose, or the opponent will choose the E. And we call the player that's first starting the game over here is called the maximizer, and this is a person who is trying to maximize the utility. He's trying to go to the maximum utility he can achieve in this game. And the second person is called the minimizer. So there is a maximizer turn, and then there's a minimizer turn. And the minimizer tries to minimize the utility. And we need to consider the minimizer's choice in order for us to get to the maximum utility that we can. So in this is basically a backtracking algorithm where if you know how the game goes, okay, and mostly we do know how the games go, like the tic-tac-toe. If you select this, then you have choices that you can do, and then you can play as you go on. So there are a finite number of choices that you can go from state S, and then we could actually draw the tree and then from the tree we can get the utilities of all the leaf nodes that are here at the end, and from that we can actually determine which choice we can actually go to. So this is a very good strategy that we came up with as we were discussing, and this is called the minimax strategy. It's minimax because you have the maximizer and you have the minimizer. So the minimizer is going to try to minimize and the maximizer is going to maximize. So what's going to happen is we know that the game tree is like this, and before we start the game we can come and say, well, if I was the minimizer here, what I'm going to select for A? I'm going to select the utility of 2. So A has a utility of 2. What am I going to select if I was at B? I'm going to have E with utility of 1, so B has a utility of 1 because I'm a minimizer, so I'm going to select the minimum, so the minimum of 2 and 7 and the minimum of 1 and 8. And then the maximizer will have the selection between the utility of A, which is 2, and the utility of B, which is 1. So the maximizer is always going to go to A and select the maximum utility, which is 2. So the game will always end up being played at this path if two intelligent agents were playing it. Okay, so this is what we are trying to explain over here. So I already explained this in the previous one, so I'm just going to go over this very fast. Again, what you're trying to do is to maximize the utility for the maximizer, and the minimizer is trying to minimize the utility. Okay, and that's how the game actually goes. So let's take a bigger game, a little bit bigger game, where you have the maximizer, then you have the turn of a minimizer, then you have a turn of a maximizer, then you have a turn of a minimizer. So it's a fair game. Everybody has two goes, and each time you have two choices. Okay, so this is basically what's happening over here, and at the end we'll give you the utility of all the different states that we have. So the final state over here has a utility of 8, this state has a utility of 7, this state has a utility of 3, this state has a utility of 9, going on all the states as you can see over here on the slide. These are the utilities that you can get to. Okay, and as you can see, the maximum utility is 9 and the minimum utility is 1. So the maximizer, if it doesn't do any type of calculation, and if you are playing this game, you will look at the maximum utility, which is 9, and the minimizer will look at the minimum utility, which is 1, and then the game can actually start. Now, how would you, as a maximizer, select which path are you going to select, the left path or the right path over here? So this is what the question is. Which one is going to bring me more utility? To do this, let's do this by hand. Okay, so let's say we have 8 over here and 7 over here, and I am a minimizer here. So the minimizer is going to try to minimize the utility, so it's going to select the minimum of this. So the utility of this node becomes 7. Okay, so if I am at this node, the minimizer will always select this path to go. Okay, for the same thing for, now we have 3 and 9. For the 3 and 9, the minimizer is going to select 3, so the minimizer will select this path. Okay, it's never going to select the 9, it's trying to minimize the utility of the maximizer. Similarly, for 9 and 8, the minimum is 8, so this is going to give you a utility of 8. This is going to give you a utility of 2. Okay, this is going to give you a utility of 1, minimum of 1 and 8, and this is going to give you a utility of 8, because 8 and 9, the minimum is 8. This one is going to give you a utility of 9, and this one is going to give you a utility of 3. Then the turn of the maximizer is going to be before that. Okay, although the game has not been played yet, but this is how the game will eventually go. So the maximizer will have a choice between 7 and 3, so it's going to choose the maximum, so it's going to go to 7. Okay, so this will become 7 because I am going to check this path. And then from here, the maximizer is going to select an 8. Okay, so this is the path that the maximizer is selecting. And going on, the maximizer is going to be putting an 8 over here. Okay, and then it's going to be putting a 9 over here. So if I was the maximizer, I will go to the maximum number. Then the minimizer is going to select the minimum of these two. So it's going to select a 7, and that's the path it's going to select. Okay, and then the minimizer over here is going to put an 8. Okay, and that is the path that it's going to select. And then as a maximizer, okay, of course, let me put the arrows over here where we were going, and this was 8, and this was 1, and this was 9. So over here it doesn't matter, you can select any because they're tie, and this one is over here. Okay, so what will happen at the end state is 7 and 8. I'm going to have the maximizer is going to be selecting an 8. Okay, so it's going to be selecting an 8 because I'm maximizing, so the game is going to go this way. Okay, so what we're saying, the game is going to go this way, then the minimizer is going to go this way. So any smart agent playing this game who can actually make this tree will go to the to this, and then the minimizer is going to shift me here, and then the maximizer is going to shift me here, and then the minimizer is going to shift me here, and that's how the game is going to be played. Let's do this again with another visualization. So in the first level, the minimizer, notice the minimizer is going to take the minimum of the choices it has in the below state, and then get to 7, 3, 8, all of these numbers. Then the maximizer is going to come into play. The maximizer is going to take the maximum numbers, and the maximum numbers between the choices that is below it is going to be 7 and 3. The maximum is going to be 7, and between 8 and 2, the maximum is going to be an 8. Okay, and going on all these different choices that we have, these are the values that we get. Then the minimizer is going to come, and he's going to select the minimum of the level that's beneath it, and that will make it 7 and 8. And then the maximizer is going to select the 8, and this is how that game would go eventually if 2 smart agents were playing this game. Now this is something similar to what we actually see in real life. So when you play tic-tac-toe in the beginning and you don't know these trees, you might lose, you might win until you get trained enough in it. And when you get trained enough in it, you actually end up with a tie in the tic-tac-toe game. And that is the reason that there are only a finite way in the tree of a tic-tac-toe game where you could actually go to a tie that you're going to be selecting. So if you're looking at the maximizing and minimizing, there are a few choices that you are selecting. You start from maybe the middle, and then you have a state of the board, and then you can actually branch down with the different states, and you would see that every time you will plan to go to win, and then you will find that, hey, I cannot win, I have to block. And then once you start blocking, then the other opponent will start blocking, and then the game ends in a tie. Okay, so that's what happens when experts play the game. Nobody actually wins in tic-tac-toe. It's always a tie. And that is for the same reason. So you end up having few paths that you can actually select. Now, of course, this is a very small tree. The tic-tac-toe game, in the first level, the maximizer has 9 choices, so the tree is quite big, and then the minimizer has 8 choices in the next level. Okay, so the tree is bigger, but eventually, when you start the game, you are selecting one sub-branch of this tree, and then you are digging down in that tree, and then trying to find, the computer is trying to find, well, which state can I actually win, and which states will get a tie, and which states I will lose, and it's trying to head towards the winning unless it comes to a state where it has to lose, then, or a tie, then it's going to select the tie state. Okay, so that's basically what's happening in the game. So here is a very small code that the Minimax algorithm uses. This is again a pseudocode, and this is the function name. So let me over here select the pointer to be the laser pointer here. So this is the function, the Minimax. It takes the input, the number of nodes that you have, the depth that you want to search to, and the maximizing player. Who's the maximizing player? Okay. So when we start, we check if the depth is 0. What depth 0 means is that, hey, do not do anything, do not look into the tree, and just take the choices. So the node is a terminal, then you don't have to do anything. You just make a heuristic guess of where you want to go, and you just select anything at random, basically. If the depth is not 0, okay, so basically you want the computer to take more steps down, look ahead. Look at the steps that the adversary will do in the future, and you put a number for it, and you are the maximizing player. So what we do is we set the value to the least possible, which is minus infinity, okay, in this case. And then for each child node, what we do is we get the maximum value for the minimax for the child for the depth -1. So if you are looking for depth -3, so you go, if you're looking for a depth of 3, so you go and call this function, which is calling the same function, the max function. You're calling the minimax function basically over here with the child with 1 less depth, so it's a recursive function again, and you're making it false, so you are not the maximizing, you are the minimizer. Okay, so the next time you go in and you can, is maximizer player? No, it's not the maximizer, so you go, hey, this is a minimizer player, and the minimizer player will put the value to be plus infinity because I'm trying to get the minimum value, so I'm going to set myself to infinity, and for each child I am going to check the minimum value of the value that I have, which is plus infinity, and the minimum, the value that the minimizer is giving for the depth -1. So at now the depth is 1. And then go ahead and when you reach 0, you return the heuristic, or the value that is the utility of the node itself, and recursively these will be given back to the minimizer, to the maximizer, and then the maximizer would know how to which choice to select. Okay, so this is a very small recursive code that is trying to solve the minimax algorithm. As you can see, dynamic programming is playing a lot of role over here. We don't have to write multiple if-else statements over here. Why? Because we're working in a recursive manner, so we're calling the same function again and again recursively, and we're trying to solve this problem with a depth lower. So notice when we start with a depth of 3 and we're the maximizer, we're going to make the depth of 2 and we are the minimizer. Then the depth will become 1 and I'm going to become the maximizer. Then the maximizer will have a depth of 0 and I'll become the minimizer. And when I come to the 0, notice I return the heuristic. Then the maximizer is going to get the value, then send it to the minimizer, then the maximizer, and you will get the same tree generated again. So the recursive function generates the tree as it goes. So this is how this code is going to be working. It's a pretty small piece of code, but it can actually solve any minimax type of problem, and it can explore the entire tree of the solution and get you with the best solution that's there. So this is the end of this video. I thank you very much for watching this video, and I hope to see you in another video series soon. Bye bye.